Okay, welcome back. We're going to finish up Chapter 10, Unit 6 here with the following targets. I can interpret a probability distribution and answer questions based on the graph, and I can find the probability of a given binomial event. Have these targets in your notes for tomorrow. Okay, the histogram, you're interpreting a probability distribution graph. So we're going to get probabilities from graphs this time. In this section. The histogram shows the probability distribution for the sum when two four-sided dice are rolled. The 16 possible values of the sum are the integers from 2 to 8. So if they have the integers 1 through 4 on the sides, here are the possible combinations and sums. All the way from 1 and 1, which is a 2, up to a 4 and 4, which is an 8. It's represented on the graph over to the side. So what is the most likely outcome for rolling the two die? Well, what's the tallest bar? The tallest bar is 5. So the most likely outcome is a 5. What is the probability that the sum of the two dice will be 7? Well, if I look on my chart, 1 out of 8. So 1/8 chance. What is the probability that the sum of the two dice will be even? Well, for C, we're going to add a little bit. Even numbers are 2, 4, 6, and 8. So it looks like we have 16 values here. If you're going to get a 2, there's 1 out of 16 to get a 2. See, that's half of 0 to 1/8. To get a 4, which is the other possibility, that's 1 16, 2 16, 3 out of 16. You can also count them 4. There are 1, 2, 3 out of 16 ways to get a 4. 6, there's also 3 out of 16. There's 3 6s up there. And to get an 8, there's only one way to get that. So when I add those all together, I get 6 16ths or 3 8ths. And then what is the probability that the sum of the two dice is at most 4? So that's 2, 3, or 4. The probability of getting a 2, that's 1 out of 16. The probability of getting a, oh, I'm sorry, I added that up when I was doing the next one. It's not 3 8s, what am I saying? That would be 3 6 8 out of 16. My bad on that one. Sorry about that, but I think he added wrong. I made that mistake on purpose to make sure you're paying attention. So it should have been 1/2. Half the numbers are even. That should pretty much make sense. They're all equally likely. 1 out of 16 for getting a 2. So back here on this one, at most 4, that's a 2, a 3, or 4. So we're going to add those together. 1 16th. To get a 3, that is 1/8 or 2 16ths, just to keep like denominators here. To get a 4, that is 3 16ths. That is 6 16ths, which is what I have for the last one, or 3 8. Okay, so that's using the graph. We'll use actually drawing out the outcomes to do some probabilities. So let's look at this example. The histogram shows probability distributions for choosing a specific letter block from a bag which contains 21 total letter blocks, 7 A's, 3 B's, 6 C's, and 5 D's. So I'm going to trace over this histogram here just so we can see the bars, because it might be kind of hard to see the way it copied on the screen in black and white. Okay, but that's the height of the bars here. So what is the most likely outcome in choosing a block? Well, the tallest one is A. So choosing A is the most likely. What's the probability that block C will be chosen? Well, block C has a 2 out of 7 chance of being chosen, 2 7ths. What is the probability that block D will be chosen? The probability that block D will be chosen, well, that's kind of hard to tell, right? Because it's between these two. So we have to look and say, what is our intervals that we're going by here? Well, if this bar is 2 over 21, then that means that first one is 1 out of 21, right? So these are going up by 1 out of 21. So 1, 2, 3, 4. This would have to be 5 out of 21. So 5 21s. So that would be the answer for that one. What is the probability that either block A or block B? So that's A plus B. Probability of A, that's 5, 6, that's got to be 7 out of 21, right? So 7 out of 21 plus B would be 1, 2, 3 out of 21. So 7 out of 21 plus 3 out of 21, well, that would be 10 out of 21. Okay, so now we're gonna switch gears from looking at the graphs and finding probabilities, which that happens quite a bit. Reading graphs or interpreting, maybe not necessarily for probabilities, but you're going to interpret graphs a lot in the real world, reading the paper every day. We're going to switch gears from that, though, to binomial experiments. A binomial experiment meets the following conditions. There are n independent trials, so there's a finite number of trials. Each trial has only 2 outcomes, success or failure. And you can determine which one is a success or a failure. It depends on the situation or which side of the coin you're looking at. But heads or tails on a coin, true or false, right or wrong, you can look at it that way as well. The probability of success P is the same for each trial. So every time you have the same probability for success. The true and false and heads or tails is 0.5 for success every time. If you have a multiple choice test with 4 answers each time, and each question is 4 possible solutions, 4 answers, choices, then you have a 1 out of 4 chance for each to get it right on each of those questions. The probability for failure is 1 minus P. So for that last one, you have 1 minus 1/4. If there's a 1/4 chance of getting it right, you have a 3 out of 4 chance for getting it wrong. 1 minus 1/4. And the probability of K successes and N trials is N CK, or combination, taking N things, taking K at a time, times the probability of success to the K power times the probability of failure, or 1 minus P to the N minus K power. It looks really hard, okay, but it's not so bad. So this is the number of trials in your experiment. K is the number of successes. Okay. P, that's the probability of success. Probability of success. This is the probability of failure. 1 minus P part. Okay, and N minus K, that's subtracting the number of trials minus the successes. It's really the number of failures. Okay? So, keep that in your notes as we move forward here. Okay, let's try a couple examples, actually calculating binomial probabilities. If you toss a coin 10 times, what is the probability that you will have exactly 3 tails? This is a binomial experiment because you only have 2 possible outcomes. So let's label all these pieces. N is the number of trials. How many times do we flip in the coin? That's 10. K, how many successes do we want? We want exactly 3 heads. Right? Excuse me, 3 tails. Same difference either way though. The probability of getting a tail is 1 out of 2 with 0.5. The probability of failure, or 1 minus P, is 1 minus 0.5 or 0.5. So that's really the only time that the failure and success rates are going to be the same, if they're both 0.5. And then our number of failures is 10 minus 3 or 7. All I'm going to do is plug these numbers into this formula. Okay, sorry about that. So now we're going to plug these numbers in. 10 is 10, so 10 things, choose 3 times the probability of 0.5 to the 3rd power times the probability of 1 minus 0.5 or 0.5 to the N minus K or 7. Okay? I'm actually going to erase it. I'm just going to put 0.5. We already calculated that, but you can just plug it in as the raw numbers. So now we just go to our calculator and we put this all in. So I type in 10 things, math, We're going to do probability, PRB. We are going to choose 3 times 0.5 to the third power. And then times 0.5 to the seventh power. And we get 0.11875. If we want that as a fraction, we hit math, fraction, and we can get it in either form. So probability of getting exactly 3 heads, or 3 tails, I guess in this case, 3 tails, when we flip the coin 10 times is 0.12 or 15 out of 128. Here's a fun one. If you take 25 question true-false test, what is the probability you'll have exactly 22 correct answers, assuming you just guess and you don't know any of the answers. So n equals 25, k equals 22, p equals 0.5, 1 minus p is 0.5, and n minus k is 25 minus 22, or 3. So once again, we have a probability of success at a true-false question of 0.5. That's why it's probability of success is 0.5 again. We do 25C22 times 0.5 to the 22 times 0.5 to the 3. Put that in your calculator, and you're going to get, well, you're going to get a really small number. You're going to get 6.85. It's going to say E negative 5. And what that really means is take 6.585 and move the decimal points 1, 2, 3, 4, 5. So you do not have a very good chance of just guessing and getting 22 out of 25 correct on a 25 question true false. It's just a test. Okay, so make sure you study next time you have a true false test. Okay, last one. This one a little bit more fun. ACT is getting closer here, or may have happened already, depending if you took it already. But let's say on the ACT you said, hey, it's multiple choice. I don't guess. I can get 48 out of 60 correct on the ACT. Well, let's see just what the likelihood of that is happening. We have n equals 60 distinct trials. We want to have 48 successes. The probability of success, there are 5 choices on the ACT, only one of them is correct. 1 out of 5 is a 0.2 chance. The failure rate, rather high on this one, 0.8. And the number of failures, well, that's 60 minus 48, or 12. When we plug this in, what do you think it's going to be? We're going to have a high likelihood or a high probability of guessing and getting 48 out of 60 right, which would be a very good ACT score if you could do that. Let's plug it in our calculator and see what we get. 60, math, probability, 3. 60, we're going to choose 48 out of 60 things. We're going to multiply that by 0.2. The 48th power, close that parenthesis, to the 48th power, and then times, let's see, 0.8 to the, oh, it's 12th power, right? Get an answer. So, here it is. 0.27 times 10 to the negative 23rd, remember that scientific notation. So we take that decimal point from right here, we move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Well, you get my point. Is there a likelihood that we're going to just guess and get 48 out of 60 right on the ACT? And the answer is no. And this is why this is a standardized test, and it's validated because you can't, it's very hard to just guess and get a good score. They did that on purpose. That's why it's used to let you into college, or get you accepted into colleges, is they want to know that you legitimately can be successful or not in a college course. Okay, did we hit our targets today? I think we did. We interpreted probability distributions, the graphs that we did, histograms, and we answered questions based on the graph, and we found the probability of a given binomial event using the formula we just learned about today. Have these notes ready to be checked tomorrow. We'll see you then.